Near-Earth asteroids are always moving, and most of them never come close. The tense moment begins when we discover one and realize we do not yet know its path with perfect precision. Danger is not a vibe, it is a calculation that gets updated as new observations arrive. For planetary defense, three numbers matter more than anything else. Size tells you how much material is involved. Speed tells you how much energy that material can deliver. Trajectory tells you whether Earth is actually in the way and how much time we have. Here is why asteroid headlines can sound dramatic. In the first days after discovery, astronomers may only have a short set of observations. That creates a wide spread of possible future paths. When more data comes in, that spread shrinks, and the risk estimate can jump up or down before it settles. So, let's do the countdown. By the end, you will be able to hear an asteroid headline and immediately ask the right questions. One more thing before we start. These numbers are not only for scientists, they are a translation tool. If a headline says a rock is the size of a bus, you can ask, how fast and on what path? If a headline says a rock is the size of a stadium, you can ask the same questions, but now you already know the stakes are very different. Close approaches also confuse people. A rock can pass closer than the moon and still be perfectly safe. Space is big, and even a close flyby can still be a huge miss. The real question is whether the trajectory line actually crosses Earth at the same time Earth is there. Sometimes time is the hidden fourth factor. A small impact probability for next month is a bigger concern than a higher probability for 60 years from now, because time is what allows better tracking and, if needed, a response plan. The first number is size, usually an estimated diameter. Size matters because mass grows fast as objects get larger. If you double the diameter, the volume becomes about 8 times bigger. More volume usually means more mass, and more mass means more potential impact energy. But early on, size is often a best guess. A newly discovered asteroid might look like a faint dot. Astronomers measure its brightness, then estimate how big it might be. The problem is that brightness depends on size and on how reflective the surface is. A dark asteroid can be large but look dim. A brighter surface can be smaller but look obvious. That is why early reports often give a range. As observations improve, the size range tightens. Infrared measurements can help because they measure heat, not just reflected sunlight. Radar, when available, can also sharpen the picture. The asteroid did not change, the measurement did. You may hear the phrase, potentially hazardous asteroid. That label does not mean impact is expected. It usually means the orbit can come close to Earth's orbit and the object is large enough to deserve attention. It's a watch list label, not a prediction. Size tells you how much stuff. Speed tells you how hard that stuff arrives. Impact energy depends on mass and on speed squared. If speed doubles, energy becomes 4 times larger. So 2 asteroids of the same size can have very different consequences depending on their impact speed. There's also a minimum speed for anything that actually reaches Earth. Earth's gravity pulls objects in and accelerates them. By the time an object reaches the atmosphere, it would be moving at least about 11.2 kilometers per second relative to Earth, and many impacts are faster than that. Typical impact speeds for asteroids are often in the tens of kilometers per second. Comets can be faster. At the extreme, there is a physical limit for objects orbiting the Sun, around 72 kilometers per second. To see what a modest-sized object can do, remember the Chelyabinsk event on February 15, 2013. A small asteroid entered the atmosphere and exploded in the air. The blast wave shattered windows and injured many people, mostly from broken glass. It didn't need to hit the ground to cause real harm. So speed answers the question, if this arrives, how much energy arrives with it? Earth's atmosphere is part of the story. Some objects break up high and produce a bright fireball with little damage. Some explode lower and create a shock wave strong enough to break windows. Some survive deep enough to deliver heat and pressure close to the ground. Some strike the surface and excavate a crater. This is why two objects with similar size and speed can still lead to different outcomes. Strength matters. Angle matters. The altitude where the energy is released matters. It also explains why casual labels can mislead. The safer way is to focus on measurable values and updated probabilities. Trajectory is the "will it actually hit" number, and it is where most uncertainty lives. When an asteroid is first discovered, astronomers calculate its orbit from a short arc of observations. With limited data, many slightly different orbits can match what we have seen. That creates a corridor of uncertainty into the future. Monitoring systems take that corridor and search for future close approaches where Earth and the asteroid could arrive at the same point at the same time. Systems like NASA's Sentry and the European Space Agency risk lists are designed to scan and update these calculations as new data arrives. Their job is to keep a running score based on the best available observations. Here is the calm point. A non-zero impact probability often means we do not yet have enough data. As follow-up observations come in, the uncertainty corridor shrinks. In many cases, the probability drops to zero and the object is removed from risk lists. That is not a reversal. That is the system doing its job. A real example helps. In January 2025, reports discussed asteroid 2024 YR4 with an impact probability above 1% for a possible impact date of December 22, 2032, while also emphasizing that the much more likely outcome was no impact and that the probability would change as more observations arrived. Trajectory answers two questions at once. Does the orbit intersect Earth at a future date, and how much time do we have before that date? Think of the asteroid's future path like a wide lane painted in the sky. In the first days, that lane is wide because the orbit is uncertain. Earth is a moving target that crosses that lane at certain times. As astronomers collect more measurements, the lane narrows. Sometimes, while the lane is narrowing, Earth stays inside it for a particular future date. The result can be a temporary rise in impact probability. It is not because the asteroid suddenly turned toward Earth, it's because the math is squeezed down to a smaller set of possibilities that still includes Earth. Keep observing, and in most cases the lane narrows again and shifts off Earth. Then the probability falls, often to zero. That rise and fall is a normal feature of early uncertainty. All three numbers can improve. Survey telescopes find moving objects, then follow-up telescopes measure their positions again and again. Each new measurement tightens the orbit. The longer you track an object, the better the future path becomes. For objects that pass close enough, radar can measure distance and speed extremely precisely. That can transform an uncertain orbit into a well-known one and extend reliable predictions far into the future. Size can also improve with infrared data, which helps separate size from reflectivity. The bigger goal is simple: find more objects earlier, track them longer, and reduce uncertainty. Trajectory is also warning time, and warning time is everything. A small push applied years in advance can grow into a large miss distance by the time the asteroid reaches Earth's orbit. That is why early detection changes the conversation from emergency reaction to planned response. NASA's DART mission tested this idea by striking a small asteroid moonlet to change its orbit. The results showed that kinetic impact can measurably alter an asteroid's motion, supporting it as a practical method when there is enough warning time. Planetary defense is also global. Sharing observations and orbit calculations helps everyone converge on the truth faster. Next time an asteroid alert hits your feed, ask for the three numbers. First, size. What is the estimated diameter and how wide is the range? Second, speed. What is the estimated impact speed and what does that imply for energy? Third, trajectory and time. What is the impact probability? What is the possible date? And how uncertain is the orbit right now? Watch the trend. Is the orbit getting better defined? Is the object staying on a risk list or being removed after follow-up? That is the scoreboard. 3 numbers: size, speed, and trajectory. The better we measure them, the less likely it is that we will ever be surprised by what is moving through our neighborhood in space. Scientists also use simple risk scales to communicate. One public scale is the Torino scale, which groups events from routine to serious based on probability and expected impact energy. A technical scale, called the Palmero scale, compares a risk to the background chance of impacts over time. Early energy numbers can be rough because density and structure are often unknown initially.